Hi there. Welcome back to the formulaic approach. And Merry Christmas. I'm shooting the video on a Christmas day. Do want to subscribe to the channel. Today we'll be talking about benzene. And I'm going to deal with many things about benzene, beginning from what benzene is, aromaticity, the concept of aromaticity. You are going to understand that concept by the grace of God in this video, I promise you. Then, of course, we are going to deal with the synthesis and chemical and physical properties. So, and of course, IUPAC nomenclature. Okay, so make sure you stick till the end. So, if there is a particular thing around what I've just mentioned that you want to watch, you can skip to that part of the video. All right. So let us go from the beginning, of course. I like to build it up from the beginning. So now benzene is a particular hydrocarbon, okay? Benzene is a particular hydrocarbon that belongs to a family, belongs to a family that is called or belongs to a class of hydrocarbons called aromatic hydrocarbons. Okay, aromatic hydrocarbons. Now, I've discussed this in my introduction, of course, what aromatics are, but I'm going to talk about them again now. Now, you see the aromatics. So, from the name first, you can tell already that it has something to do with their smell, right? So, the name was first given when certain chemicals that were extracted from oil-producing plants gave good smells. Okay, so that name aroma came from that. Okay, so that's aromatic. But now the name aromatic is much more reflective of their structure than it is their physical property. So that's just it, aromatic hydrocarbons. So that is the general family in which this benzene belongs to. Okay, benzene is the most, could I say most important or the most common, right, that you will see under the aromatic hydrocarbons. So now, another thing you should know is that they have a general formula. They have a general formula CnH2n minus 6y or minus 6x, depending on the textbook you're using. Now, where that y or x represents the number of rings that are available in the structure. So this is their general formula. I said benzene belongs to what? A class of aromatic hydrocarbons, and general formula is what? CnH2n minus 6. And I told you that aromatic hydrocarbons, the aromatic hydrocarbons are what? They are generally, they are unsaturated, they are cyclic first. That's the first thing you know about them. They are cyclic, okay? They are cyclic. Then unsaturated hydrocarbons, okay, that are generally stable and non-reactive. So hydrocarbons that are what? That are generally stable and unreactive. Generally stable and unreactive. Okay, so now then you tell me, how about the chemical properties I want to discuss? Now, of course, we know they are reactive, but it takes a lot of effort to get them to react. So, for example, you need a very strong, reagent, a strong organogen to get them to actually react. So they are generally stable. All right. Now that's what separates them from general alkenes. Okay, they are unsaturated, but they are generally unreactive and more stable than the other unsaturated guys, alkenes and alkynes, right? So they are more stable than those guys, alkenes and alkynes. Now, and this is one of the major things that led to the concept that led to determining the structure of benzene, okay, that made them to, disagree with the first structure that was proposed by Auguste Kekule. Now let's quickly do a brief history, okay? So that a brief history. Now, benzene was actually first synthesized by a certain in 1825 by Michael Faraday. So Michael Faraday was the first guy that synthesized benzene in illuminating glass. Okay, now then another scientist with the name Hillard Michelich. Okay, in 1834 also produced benzene from benzoic acid. Synthesizes from what? Benzoic acid and lime. Okay, from benzoic acid and lime. Okay, and we're going to learn that process, of course. Then another scientist, A.W. von Hofmann, in 1845 also produced benzene. Okay, he also produced benzene from as a coal tar extract. Okay, as a coal tar extract, he produced it from coal tar. Now, but up until this moment, the structure of benzene was not yet known. But it was in 1865, so if you did not learn anything about this date, you must remember this one. I've seen it asked in O-level exams before. So, in 1865, a certain Auguste Kekule, you have heard it before, Auguste Kekule, this is by far the most prominent scientist when we talk about benzene, because he was the one that first propounded the structure of benzene. So in 1865, Auguste Kekule gave the structure of benzene. So he posited a structure, okay, a structure for benzene. So, and his structure was this. Now let's talk about the structure of benzene. The structure of benzene. First, let's talk about the structure according to Auguste Kekule. Now, the structure looked something like this. The structure looked something like this, and he propounded that the benzene ring is fully unsaturated. Now let me draw this in full for you, so that the full outline is something that looks like this. Okay, just for understanding's sake. For the rest of the video, I'll have to be drawing the ring, sure, because it's faster. So he said that there is that the benzene ring has, what do you see here first, in fact? What you see is there's alternating double, single bonds, right? Okay, so it has 6 carbons and 1, 2, 3, 4, 5, 6 hydrogens, okay? So it has alternating single and double bond, okay? So now, what does, if you have seen my video on alkene, which I'll link in the description, I've told you about when there's alternating single and double bond. Alternating single and double bond. Single, double bond. What is it called? It's called conjugation. Okay? Conjugation. So we call this system this ring a conjugated ring, okay? The conjugated ring. Now, he said that, he also said that since we understand in conjugation that the ring, the pi bonds that make up these electrons here, the pi bonds, are able to, resonate, okay? The concept of resonance was not known as at then, okay? But what he actually said was that there are 2 possible structures, this or this. And according to him, benzene was either like this or like this. Now we'll soon learn that these are canonical structures, but before then, those terms were not known, okay? Those terms were not known. And I'm going to tell us something about it, so you just stick with me. Now, when he propounded this structure, further experiment was used to invalidate his claim, okay? And some of the findings from those experiments were, number one, that this guy, when a carbon is unsaturated, when a hydrocarbon is unsaturated, what's the test for unsaturation? Test for unsaturation. Now, apart from the one that I provided for alkynes, that was unique to alkynes, there are two major tests for unsaturation. The first one is what? Using bromine water, right? Using bromine water. And the second was using Bayer's reagent, right? Bayer's reagent. And that's KMNO4, right? Now, and what does unsaturated hydrocarbon, what do unsaturated hydrocarbon, what do they do to these two guys? They decolorize them. They decolorize them. So, but the argument of the scientists was that benzene, when reacted with these guys, does not decolorize them. In fact, it doesn't react with them under the same condition for alkenes. Do you understand? So, if it doesn't decolorize them, then this structure is probably wrong. Is that okay? Because this is on saturation here. So why is it not decolorizing this guy? Why is it not reacting like an alkene, which will naturally decolorize bromine water and Bayer's reagent? That was the first argument. Now the second argument was that the bond length, I've told you about bond length before when I introduced you to organic chemistry. I told you bond length for carbon to carbon single bond, sigma bond. The sigma bond is 1.54 Armstrong or 154 picometers. Is that okay? 1.54 Armstrong or 154 picometers. Then for carbon to carbon double bond, okay, we have 1.34 Armstrong or 134 picometers. Then for carbon to carbon triple bond, we have bond length of 1.19 Armstrong or 119 picometers. Now, this is the bond length this is the bond length for each of the types of bonds, single, pi, and double pi's. Now, what is now the case with with benzene? Benzene bond length in benzene, number one, you know, if this was true, bond length should be, for this guy, it should be what? 1.54 Armstrong. For this guy, it should be what? 1.34 Armstrong. For this guy, 1.54, 1.34, like that, right? But it was discovered that bond length in benzene was the same. All through, throughout the carbons, throughout carbon atoms. And what was the bond length? It was discovered to be 1.39 Armstrong. 1.39 Armstrong or 139 picometers. So this was the bond length that was discovered for benzene. So which negates the single bond or the double bond bond length. Okay, so it means that the bond length of benzene is neither that of sigma or that of pi's. It was somewhere in between them, right? So you know, that was another argument that was put forward against his claim for that that structure for benzene. Now, another thing that was discovered, another argument that was put forward was that benzene structure could be substituted in different ortho positions. in different ortho positions. Now I'm going to tell us what ortho position is, okay? I'll tell us what the ortho position is. So, but it was, so he said that, they said that the guy could be substituted in different ortho positions. Now let me tell you what that means. So two possible structures were therefore outlined for benzene. If you say that that is the structure of benzene, then you are saying that benzene structure could be like this. If I have, for example, I have this. Look at this. I have carbon, double bond C, then Cl or Br. Let me use Br, that is very different. Now, this is the first substitution, and the next substitution is one that looks like this. Now, if I put Br here as well, okay? No, this was, I'm going to draw the same shape, sorry. Now, one thing I did not mention is this, that benzene molecule actually undergoes their preferable reaction is called the electrophilic aromatic substitution or electrophilic substitution reaction. Is that okay? Those are two names. I'll still talk about that. Okay, so that's why when they actually got benzene to react, now it prefers to undergo substitution reaction. Now they discovered that it could be substituted in two positions, two different positions, and it will give it two different names. So if it's substituted two similar positions but different names or different molecules. So if you have this, so you see that the the bromine here and this hydrogen here, there is, let's put a molecule here. Let's substitute this guy here so that it's obvious. Now, so this guy, between this methyl group and the bromine group, bromo group, you see that there is a double bond. But between this, the same molecule, notice the structure is the same. Between this methyl group and this bromo group here, there is a single bond. Now, so that was another argument that was put forward that negated this structure that was postulated that was given by Kekule. So, and according to them, it was such that when you react benzene with bromine, through maybe electrophilic substitution, of course, through electrophilic substitution, what happens is that it forms only one type of auto substitution. So, and this one with that structure gives two possibilities for auto position or auto position substitution. So that was another negation to the that law, that structure. Now, Kekule came up with the argument that this was actually the case, that these two structures exist in dynamic equilibrium. At that time, it was thought to be that at a particular time, this guy was like this guy was like this, such that the double bond is actually moving here back and forth, and which is not exactly right. Okay, it's not correct. Now, it was afterwards. Now, what he used this concept actually to be able to counter this guy, that this guy is actually the same as this guy. Do you understand? This structure here is actually the same as this structure. Okay, so that even if it was substituted here to look like it was like the flipped version, all right. But according to him, then the concept of resonance was not understood, okay? The concept of resonance. So it was when the concept of resonance came about that this structure was explained better. Now, what is resonance? Now, Resonance occurs for a particular structure rather, if we can draw more than one Lewis structure of that particular molecule rather. Resonance occurs for a molecule if we can draw more than two. Do you understand? Two or more. Once you can draw two or more Lewis structure of a molecule without changing the relative positions of those carbons or of the atoms attached, then that substance can exhibit resonance. Okay, so due to resonance, we now know that actually this double bond, the reason why it had equal length, also is that, now you remember the concept of conjugation that I taught you in alkene. Now if I have a structure like this, for example, where there is double bond here and there is double bond here. Now I must have told you, or I did tell you, that this is 1, 2, 3, 4. This is 1, 3 butadiene. Now if I want to show you the way this structure is, this guy is actually more stable than this guy. It's actually more stable than double, single, double. Now it's actually more stable than this guy, for example. Now why is this the case? Now, okay, let's even make them 5, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now this guy is 1, 4 pentadiene. 1, 4 pentadiene. I want you to understand the concept of resonance, okay? Pentadiene. Or penta 1, 4 diene. And this one is penta 1, 3 diene. 1, 3 diene. Now, why is this structure? Now, I said this structure is more stable than this. Why is it more stable than this? This one is less stable. Now, why is this guy more stable than this guy? Now, the concept of the stability of this guy is based on resonance. It's based on what? Resonance. Now, what happens is that this guy, we can only draw contributing structures, okay, for this guy. And the contributing structure of this guy, this pentadiene, the contributing structure, that is the structure that contributes to this resonance, is going to look like this: 1, 2, 3, 4. So that we move this guy here and move this guy here. Now the truth is that we usually use this kind of arrow to depict it, okay? This kind of arrow, that is to show. So for example, if I want to redraw this, then it will look like this. I use this arrow to show that this structure and this structure are actually one and the same, okay? But this molecule, penta 1, 3 diene, does not naturally exist like this ones at a particular. That is never exactly like this, or actually exactly like this. What happens is that it exists as is the canonical. These are canonical structures, rather. These are canonical structures. Canonical structures. Okay? Now, it is actually the composite structure that exists. The composite structure. Now, what does the composite structure look like? The composite structure is a structure that shows how that these pi electrons are spread throughout the molecule. So, what that's going to look like is something like this. Okay? Okay, so this is the composite structure, and the composite structure is a structure that shows the spread of that pi electron. So because there is enough space for spreading of the pi electrons here, the molecule is more balanced. So when there is a conjugated system, it is more balanced, more stable than what? Not balanced, sorry, stable. The conjugated system, I've told you, is more stable than what kind of system would this be? This is an isolated. This is isolated alkene. Okay? So why is this more stable? I said that this conjugation, first, know that it has more to do with it is sp2 hybridized, okay, but it has more to do with available p orbital. It is more concerned about available p orbital for spreading of electrons. So if p orbitals are available enough to spread electrons, then that molecule is going to be what? Conjugated. So here, this is conjugated because there is alternating single, double. Okay, so because of that, this structure, these pi electrons can spread over a larger space. Do you understand? It can spread over a larger space for these structures. So it is the canonical structures that we are able to represent here. But in real life, what exists is the composite structure, or we call it the resonance hybrid. Resonance hybrid. So keep in mind that this is also resonance here. All right. Now another term that you hear is delocalization. Okay, so these pi electrons are being delocalized. Okay, they are being delocalized. So let me show you that in the structure of benzene. Now what happens is that in benzene, the reason why we are able to have that double bond is because of resonance. I mean, why we are able to have bond length to be the same is because of resonance. So what happens here is that we can draw resonance structures of this guy. Now this will position these two guys as they are like this. Now if I draw this like this here, now we usually put them in square brackets and put an arrow like this. And these two structures are said to be contributing canonical structures. Okay? Now, these guys are actually, in real life, they are like this. What is happening is that, I'm going to show you how resonance occurs with this guy, okay? Now, the pi electrons are actually moving around the entire molecule. So because of that, there is equanimity in spread. This structure shows that there is equal spreading of what? Of pi electrons. So because of equal spreading of pi electrons, then you see that the bond length is the same throughout. 139 picometers. Is that clear? So that's why the bond length is like that. Okay, another way we draw this is like this. Because of simplicity, we just put a cycle here. So to show that it shows better that the pi electrons are in continuous motion. Okay, they are in continuous motion. Now, I said I was going to show you how resonance occurs. Just like I did here, what happens is that this from here, the way we're able to form this is that these pi electrons, they come here, and these pi electrons come here. I've showed you about arrows before, right? So what happens is that when these electrons come here and this one comes here, then you form this structure. The same way here, I'm going to show you more about drawing arrows when I begin the concept of aromaticity. So this guy comes here. Once the guy comes here, he makes these electrons to collapse here and the electrons here to collapse here. How did I get the electrons? Always remember that a bond, when you say a bond, is formed by what? Two electrons. So these two ends, I usually put the dot on the two ends to represent the electron. So these two electrons here are the ones that are collapsing here. So think of them as these two arrowheads. Like I'm picking them as these two arrowheads, and then they are collapsing here. So when this one collapses here, forms this. When this one collapses here, forms this. When these two electrons here collapse here, they form this. Do you understand? So that's how resonance occurs there. I'm going to show you more of that diagram in aromaticity. All right. So now that we understand the structure of benzene, let us move to aromaticity. We have explained resonance. So I said what exists in real life is actually what? This resonance hybrid. So the name of this guy is what? The resonance hybrid. Resonance hybrid. Okay? Resonance hybrid. So, and I said these guys here are contributing structures. Okay? So let's go to aromaticity. Let's move to aromaticity. Now, what is aromaticity? Now, a structure is said to be aromatic if it has the following properties. Now, in fact, let's compare three usually confused terms. The term aromaticity. So I've told you before that it was from substances that have good smells. Okay, that's why it's aromatic. But now I told you now we look at it more structurally than the physical property. Now, what is aromaticity? There are three terms that are usually confused. We have aromatic, we have non-aromatic, and anti-aromatic. Let me use anti-aromatic here first. Anti-aromatic, then non-aromatic. Okay? So, but since we are focusing on aromaticity, I want to tell you the conditions for aromaticity. The conditions for aromaticity. Now, what are the conditions for aromaticity? Conditions for aromaticity. Now, the first condition is that the molecule must be cyclic or cyclic. Now, if the molecule is cyclic, what does that mean? Cyclic molecule means that the first carbon is joined or is connected to the last carbon. Is that okay? Now look at that pentadiene that we drew the other time. Look at that. If I were to draw it like this, I could draw it like this. 1, 2, 3, 4, 1, 2, 3, 4, 5. So, and this molecule here. Is it cyclic? No, because this, if I call this carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, you see that carbon 5 is not joined to this guy, right? But if I were to draw it like this, such that I have my double bond here and my double bond here. Now, what do you see here? You see that if I call this carbon 1, 2, 3, 4, and 5, carbon 5 is linked with carbon 1. So this guy is cyclic. This guy is non-cyclic. So because of that, this guy cannot even be aromatic. Okay? So this one has the possibility of being aromatic, but we'll get to that in a jiffy. Now, I've talked about being cyclic, where the first carbon must be linked to the last one. So it means that more like they must form what? A ring. It must be a ring structure. Now, the second condition is that the molecule must be planar. The molecule must be planar. Now, what is a plane? Primarily, planar molecules in organic chemistry are sp2 and sp hybridized. But in the concepts that you are usually tested on, is usually you are looking for sp2 hybridized. But I've told you, of course, that for planar molecules, that the major idea is that do we have free or available p orbitals for resonance. Do you understand? Available p orbitals for resonance to occur, for resonance. Okay, but whether or not the molecule is planar is determinable by whether it is sp2 hybridized. And which molecules are sp2 hybridized? Anyone that has double bond. Is that okay? That's sp2 hybridized. sp hybridization is triple bond. sp hybridized. This one, sp2. Is that okay? Once a carbon has double bond connected to it, it will be sp2. Now, but if a carbon has two double bonds connected to it, it will be sp hybridized. Is that okay? Not sp2 again. sp hybridized. I've explained this in the beginning in my introduction to organic chemistry. So, planar molecule, that is this sp2, and that is, we said, we mean that it should be fully planar, okay? It should be a fully planar molecule. Now, the next thing is that it should also be fully conjugated. Fully conjugated. So, it means that the conjugation must happen throughout the ring, must be throughout the ring. If it is not fully conjugated, then that molecule is not aromatic. the molecule is not aromatic. That is, it must not be partially conjugated. Then also here, I said sp2 hybridized, not sp3. Once there is a part of the molecule that is sp3 hybridized, then that molecule is non-aromatic. Then if it is not fully conjugated, it is partially conjugated, then it is also non-aromatic. Now, what does a partially conjugated ring look like? You saw that ring I drew the other time? I put my double bond here. Now, this guy is not fully conjugated, right? Because we have a double here, single here also. And then we have another double here. So this is not fully conjugated, but it's conjugated from here. Double, but single. Is that okay? So it is partially conjugated. So as it is here like this, it is not aromatic. But I can actually make this guy to be aromatic, and I'm going to show you how. Let's talk about the last condition. Now, the last condition is Huckel's rule. What is called the Huckel's rule? Now the idea of another idea of aromaticity is that the molecule is stable, is going to be highly stable at a low energy state. So now, one of what Huckel's rule helps us to do is there are some molecules that are highly stable, but they have high energy. So without having to carry out experiments, the way we can check for aromaticity is using Huckel's rule. And it is actually a formula, one of the formulas we learn in organic chemistry, which is 4n plus 2 is equal to the number of pi electrons. The number of pi electrons. Okay, so let me just put pi electrons there. 4n plus 2 equals to what number of pi electrons? Now this your n must be whole number, or should be a whole number. Now where n is not a whole number, then your molecule is what? Either anti-aromatic or non-aromatic. Is that clear? So now let me draw some structures on the board, and then we'll determine whether they are aromatic, anti-aromatic, or non-aromatic. If it is aromatic, we use this for aromatic. If it is anti-aromatic, we use this. And if it is non-aromatic, we use this. Is it clear? All right, so let me draw the structures on the board. Now let me first draw like some two structures here to show you how we use this rule. So for example, let me draw the simplest ring that we can have is this, something like this, for example. Now if I have this molecule here, now does it conform with the first one? Is it a ring? Yes. So it's a ring, so it is cyclic. Let's give you 4 marks. 4 marks for this guy, if it conforms with the 4. How about cyclic? How about being planar? Is it fully sp2? Now this carbon is sp2, this carbon is sp2. But how about this carbon? This carbon here is sp3. This carbon here is sp3, so it doesn't meet up. So this guy is what? Non-cyclic, non-planar, okay? And non-aromatic. So this guy is non-aromatic. Now, what if I don't have what is called a carbocation or a carbanion? Now, make sure that you understand this idea. Now, for carbocation, what if I have a carbocation here and I have a double bond here, for example? If I have a carbocation here, now when there is a carbocation, I've told you before that a carbocation means that a carbon that has lost electron, right? Carbon that has lost electron. Carbon that has lost electrons. So if it has lost electron, it means that there is what? A free p orbital. It means it has a free p orbital. So if there is a free p orbital, then this guy is cyclic, of course, as you can see, and is sp2 already. Do you understand? And of course, it is. Now, let's see if it can be fully conjugated. How do we do that? We have to draw the resonance structure. Now, what will happen is that this guy collapses here. When he collapses here, we have, I'm going to do a video on resonance separately. So once it collapses here, what we have is that we have a double bond here. Now, because this double bond has begun to occupy this free space here, this this free space here comes here. Do you understand? Then what happens is that another resonance structure that we can have is this guy coming to attack here. And once that happens, then you see that the double bond will move here. Once the double bond moves here, then there is a free, the cation comes here. Do you understand? The free p orbital comes here. So these are three resonance structures that can be drawn for a molecule, for this molecule. So if this is the case, let's see. So this guy is fully conjugated then. It's fully conjugated. Then what do we have? Huckel's rule. Does it follow Huckel's rule? Now, how many pi electrons do we have here? How many pi electrons do we have here? We have 1, 2. Only 2. Yes, a bond contains 2 electrons, right? So since we have only one double bond here, once you have one double bond, that will be 2 pi electrons. 2 double bond, 4 pi electrons. 3 double bond, 6 pi electrons. That's just 3 times 2, 2 times 2, and 1 bond, 1 times 2. So now, we can use the formula. We must get a whole number integer or an integer. A whole number or an integer. So if I have 4n plus 2, will give me the number of pi electrons here. How many pi electrons do we have here? We have 2 pi electrons here. By the time we solve this, this becomes 4n equals 0, n equals 0. By the time you solve this, so if n equals to 0, this is an integer. Okay, 0 is also an integer. So because of that, this guy is actually aromatic. Do you understand? This guy is aromatic. Now, another way to use the Huckel's rule is this. Another way to use the Huckel's rule is this. Know or master the fact that the Huckel's, we will call these numbers Huckel numbers, okay? Huckel's numbers. And what would those numbers be? If n is 0, Huckel's number will be 2, right? According to what we just did now. Put 0 here, this becomes 0 plus 2, that's 2. If you put 1 here, 4 times 1, 4 plus 2, that's what? 6. So these are the set of Huckel's numbers. The next one will be if I put 2 here, where n equals 1. This is where n equals 0, here n equals 1. Now, what about if n equals 2? Put 2 here, 4 times 2, 8. 8 plus 2, 10. So what do you notice? They are increasing by 4, right? The next one will be 14, the next one will be 18. Is that right? So, once you count, so if you master these numbers, 2, 6, 10, 14, 18, blah, 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 like that. Once you master this number, and you count the number of pi electrons there, you count the number of pi electrons, and they give you 2, they give you 6, or they give you 10, then that number, that molecule is going to be what? Aromatic. That's another way to solve it, instead of doing maths of equating it to the number of pi electrons you counted. Once you have counted the pi electrons and it gives you 2, 6, 10, then it ticks. It checks this box. Is that clear? It checks the box. Now, another thing you must master is that there is also another formula which is for anti-aromatic. But I'll show you that. And let me draw some molecules first. Or some structures rather. Alright, so I have drawn 10 structures on the board. This guy, that guy, and we are going to determine whether they are aromatic or not. Now, I have a list of questions on aromaticity, many structures, okay? I picked from those questions, okay? So if you want more, you can actually reach out to me on my WhatsApp number, +2349021416307. Okay. Now, but here's the deal. We are going to be determining whether these guys are aromatic, anti-aromatic, or non-aromatic. Now, I've used this as an example to show us how to determine that, to use these rules, okay? So, I didn't even mention benzene here. So I was supposed to mention, let's discuss benzene too. Let's discuss benzene too. But there was something I was going to say. Now, what if a molecule is anti-aromatic? How do we know if it is anti-aromatic? Now, it will be anti-aromatic if its own rule, Huckel's rule is 4n plus 2 for aromaticity, 4n plus 2. This one uses 4n. So it means that the possible number of values for this one, we have 2 pi electrons, 6 pi electrons, 10 pi electrons, 14, like that. So this one, the possible number of electrons, pi electrons that we can have for anti-aromatic is 4, where n is 0. We have 0, 4, where n is 1, that will be 4 times 2, that will be 8, 12, like that. Is that okay? The multiples of 4. Okay, so that's for anti-aromatic. Then non-aromatic, of course, is does not have any rule. Now, another thing you should know is that aromatic are more stable than non-aromatic, but non-aromatic are more stable than anti-aromatic. Is that clear? All right. Now let's determine for the first guy. I might have to draw resonance structure, so that's why I'm giving a space here. For the first guy there, we have a structure that looks like this. And we have to determine whether it's aromatic or not. Now, I might not draw this resonance structure for every guy, but let's first use the first row. Is it cyclic? Yes, it is cyclic. Now, is it planar? Now, if there is a carbon linked to double bond, or one that has empty p orbital, that will be sp2, right? So this is sp2, 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 sp2. How about this guy? It's also sp2 because the presence of a carbocation, remember, I told you carbocation means what? There is a free p orbital. So because of that, this guy is sp2. So it is planar, fully planar. Now, is it fully conjugated? Let's see. Of course, it's going to be fully conjugated because this guy can contribute to the resonance structure. So once this guy moves here, the electrons move there. What will happen is that we'll form what looks like this. This guy has moved here. So at the same time, this guy will move here. Do you understand? Because this guy was moved here. So once this guy moves there, this electron also collapse here, leaving the empty p orbital to be here. Do you understand? Then the other resonance structure we can have is where this guy will move here and this guy will move here. When that happens, we are going to form a structure that looks like this. Pretty much like this. Sorry. So this one collapse here, this one collapse here. Then our empty p orbital will come here. Do you understand? So we are going to move the empty p orbital to the next resonance canonical structure will look like where this guy has come here and this guy has come here. Do you understand now? So if that is the case, let's see what that will look like, please. Now, because there are some questions that will ask you how many resonance structure can be drawn in this. I'm going to teach you how to find that in video on resonance. So, but you can actually draw it from here, following what I am doing. This guy collapse here, and this guy collapse here. So it means there is our carbocation here. So then the last position it can move to is this place. So if we draw down where it moves here, then we have that 1, 2, 3, 4, 5. So it has 5 resonance structures. Do you understand? We're able to draw 5 resonance structures rather. Alright, so the point is that we're able to move it around like that, then it means it is fully conjugated. Fully conjugated. So fully conjugated, then does it follow Ockel's rule? How many pi electrons do we have here? We have 1, 2, 3, 4. Is 4 part of our designations here? Now, is 4 part of our designations here? No. Is 4 part of our designations here? Yes. So this guy is not aromatic, it is anti-aromatic. I said we use this sign for anti-aromatic. Okay? So for anti-aromatic. So that guy is anti-aromatic. How about number 2? You see that number 2 is similar. Number 2 is very similar. Only that instead of a carbocation, we have a carbanion. Now when we have a carbanion, it means we have what? We have lone pairs. We have a lone pair. So since there is a lone pair here, it means that in this case, when we are drawing the resonance structure, these lone pairs can contribute to the resonance. It can contribute to the resonance. So what that means is that where this lone pair attacks here, what will happen is that this guy will shift. So we'll have something that looks like this. Once the lone pair attacks here, then this guy shifts here. Okay? It shifts there. Then this guy will form a lone pair here. Do you understand now? So that we have alternating single, double, single, alternating single, double, single, double. Then this will be A lone pair. So once there's a lone pair, remember, a lone pair can contribute to the resonance structure. Then we have what again? Another resonance structure is where this guy, the double bond, attacks here. I mean, the lone pair attacks here. Once the lone pair attacks here, this guy moves here and this guy moves here. What does that look like? This is going to look like this. I'm not drawing all the resonance structure because we are not focusing on resonance here. But I want you to see that it can actually resonate like that. That double bond, that the lone pairs can also help in resonance, participate in resonance. This guy moves here, then this guy comes here. Now, instead of this guy to actually move here, what will happen is that this guy will now form the lone pair, to form the lone pair here. This is where the lone pair is moving now. This is where it's moving. By the time I draw another resonance hybrid, you see that the lone pair keeps moving around like that. Now, what does that show you? This shows you that this guy, since it can be delocalized like that, it has what? It is planar and it is what? sp2 hybridized and it is fully conjugated. That's what I was going to. It is fully what? Conjugated. Now, if that's the case, now how about Huckel's rule? Does it follow Huckel's rule? Huckel's rule says that 4n plus 2 should be equal to the number of pi electrons. How many pi electrons do we have here? These are pi electrons. 1, 2. Is that clear? 1, 2, 3, 4, 5, 6. Is 6 part of our number? Yes. Then this guy is what? It's going to be what? Aromatic. So this guy is aromatic. But of course, I showed you how to also calculate this. You can also say that 4n plus 2 is equal to 1, 2, 3, 4, 5, 6, 6. Once this guy, n, can give us a whole number, then this guy is what? This guy is aromatic. So we have 4n equal to 6 minus 2. So therefore, we have 4n equal to 4. N equals 1. So this is a whole number. 1 is a whole number, for which reason we know that it follows Huckel's rule. If you use this method, just make sure that n gives you a whole number. If it gives you a fraction, then it is not aromatic. Is that okay? Right. How about this guy? Now you're also going to see in this case, it is also cyclic. Yes. There's also planar. Yes, fully planar. You're going to see. And there's also alternating single bond and double bond. Double, single, double, single. Now, how about, does it follow Huckel's rule? And of course, you can also show that it has resonance hybrid. So for example, for 3 now, we have this guy. His resonance hybrid is going to look like this guy comes here, this guy falls here, and when that happens, we're going to have this guy has collapsed here, this guy has collapsed here. This is, so by the time we have only 2 resonance structures, resonance hybrid structures for it. 2 canonical structures. Now, why are they 2 canonical structures? Because if this guy collapses here, this one collapses here again. We have the first structure that we started with. This guy has collapsed here, this guy has collapsed here. This was the structure we started with. So we have only 2 canonical structures for it. Alright, but the point is this, that this guy is cyclic, planar, and fully conjugated. How about Huckel's rule? How many pi electrons do we have here? 1, 2, 3, 4. Now we have 4 pi electrons there. Now is there 4 in our series here? No. So since there is no 4 there, you already know how to check that. Since there is no 4 there, it means that n is going to be a fraction. And we can check it. 4n plus 2 give how many pi electrons? 1, 2, 3, 4. 4 pi electrons. So we have 4n equal to 4. This guy comes here minus 2, right? So we have 4n equals 2. Divide both sides by 4. And you have that n is equal to 1 over 2. So this is a fraction. Then it is what? Anti-aromatic. Why is it anti-aromatic? Because we know that n, we know that, how many pi electrons does it have? It has 4 pi electrons, and 4 is here. 4 is here, right? In that case, the formula will be 4n equal to number of pi electrons. In this case, 4. So n equals 1. Okay? So since it's whole number 2, then that guy, this guy is anti-aromatic. Anti-aromatic. Now, how about this guy? Is this guy aromatic or not aromatic? We've done the one with a carbocation. Now, this one is with a carbanion. Now, very easy. Remember that the carbanion has 2 electrons, right? Or a lone pair. So, now the truth is also that this lone pair can also contribute to the resonance, right? To the resonance. Once this guy attacks, if he attacks here, you're going to have a hybrid that looks like this. A canonical structure that looks like this. where these are shifted here. Do you understand? And of course, you can do that for the three sides so that you have three canonical structures. So, but the point is this, that is this guy going to be aromatic? Is it cyclic? Yes. Is it planar? Yes. sp2s. Is it fully conjugated? Yes, from what you just saw. Now, does it follow Ockel's rule? We have 1, 2. 1, 2, 3, 4. So, and 4 is not in our series. So, this guy is anti-aromatic. Anti-aromatic. How about this fifth guy? Let's see. Is it cyclic? Yes, it is cyclic. Is it fully planar? Is it fully sp2? We have sp2, 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 sp2. How about this point here? This point here is sp3. So because it is sp3, this guy is non-aromatic. It is non-aromatic. Alright? How about this point here? This point here. Now what this means is that there is some form of conjugation that can happen. This guy can come here, this guy, then this guy come here. But of course, there is still an sp3 somewhere, okay? So it is partially conjugated. Is that okay? Partially conjugated. Now, how about this guy? Now, with a carbocation, then it means there is an empty p orbital, right? So it means this guy is fully sp2, cyclic, and fully conjugated because this guy can come here. In which case, the carbocation will shift around, right? If this guy comes here, this guy will also fall here, and this guy will fall here. So leaving the carbocation to move here. Do you understand now? The carbocation position will move there. So if that's the case, therefore, then this guy, how many pi electrons does he have? Let's see if it follows Ockel's rule. It has 1, 2, 3, 4, 5, 6 pi electrons. 6 pi electrons, and there is 6 here. It means n will be 1 there, right? So if 1 is, and 1 is a whole number from what we calculated here. Since that guy is the case, then this guy is aromatic. It is aromatic. How about this guy? Let's see. First, how many? We can easily just check. Is it cyclic? Yes. Is it fully planar? As you can see, it's not fully planar. This is sp3. So once it's sp3, then it is not aromatic. So let's see if it is. In fact, it is not aromatic. Okay, it is not aromatic. How about this guy? Now this guy is actually naphthalene, and naphthalene is a derivative of benzene. So this guy is aromatic, but let's check to confirm. Just check, you already know that it is cyclic, it is also fully planar, because if you check, this is sp2, 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 sp2. There's also sp2, sp2, so sp2 throughout, so fully planar. Fully conjugated, I can move this guy here, in which case this guy moves here, in which case this guy moves here. Do you understand? And in that case, it will just be the flipped version of this that will form. Exactly. So, this guy is fully conjugated. How about Ockel's rule now? How many pi electrons do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is 10 in our series? Yes. So it means this guy is what? Aromatic. Do you understand now? How about this guy? sp3 throughout, not aromatic. Exactly. Now, how about this guy? Now, this is called heterocyclic. These are heterocyclic. These are heterocyclic hydrocarbons. Now, this guy, being heterocyclic as it is, why is it heterocyclic? Because there is a different guy here, okay? There is an atom other than heterocyclic hydrocarbons have a cyclic shape, but as part of the ring, there is an atom that is different from carbon, okay? This one is called pyrrole, okay? I think pyrrole, double R. There's also pyridine. Let me draw those structures. There's also furan. Oh, yeah, furan. Furan will look something like this, where that guy is replaced by oxygen. Is that okay? So that's furan. This is furan here. Now, these guys here are aromatic. How are they aromatic? Because this guy, they are sp2 hybridized because these two lone pairs here, this one lone pair here, can contribute to the resonance. So sometimes they may not contribute because, for example, in the case of pyridine looks something like this. So in this case, there is also a lone pair here. And in this case, this guy, in this case, this lone pair does not contribute. This guy can already form resonance here. You understand? So since aromaticity is already possible here, resonance is already possible here, then these two lone pairs do not contribute, meaning that this pyridine is aromatic. This guy fluorine is also aromatic. Pyrrole is also aromatic. Then the one that has sulfur is called thiophene. Okay, all right. So that's just for aromaticity. So we're done with aromaticity. Now let's now see. We've done aromaticity and we've done the structure of benzene. Now let's see the naming. How do we name benzene? IUPAC nomenclature. Let me clean the board. All right, so now let us name benzene and its derivatives. The nomenclature of benzene and its derivatives. Okay, so one thing you must first know is that the benzene molecule has been studied for a long time before the IUPAC, IUPAC name was formalized. So, but following the formalization of the IUPAC nomenclature too, they used the common names, okay, that were already used for benzene derivatives. They use them even in the IUPAC name. So what I'll be doing is I'll be using both names, common and IUPAC, okay, so that you, whichever one you see in your exam, you're able to attend. So we have nomenclature of benzene and its derivatives. Now, of course, you should know the formal structure. I told you that the structure I'll be using is this, okay? This one where I just put an O inside, okay? This is benzene, okay? Simplistically, okay? This is benzene. Now, there is, if I have, I'm going to teach you also what is called the auto-para meta designators. But I want to auto-meta para designators. I want to first show you the common names. So I have this. Now, if I have OH attached, okay, I'm supposed to put it on, I put it here or on top, is that okay? So if this is the case, if I put OH here, for example, this is called phenol. Then someone else says, what if I move the phenol here? Now, if I move the OH here, see, whether I move the, that's what confuses students. They think it is a fixed position. It is not a fixed position. Whether I put it here, the reason why I intentionally put it down, why I put it down is actually because there's no space on top. Because what you will commonly see is this, okay? Now, the reason why we conventionally draw this for phenol is that conventionally we like to write, since OH is the only substituent in this place, which is of course the functional group, then we like to put it in this carbon, which is at the top. Is that okay? So, but actually, this is not the only structure that we can draw for the phenol. We can also put it here. This is also phenol. Once it is only one OH, it is one OH phenol. This is also phenol. This is also what? Phenol. Now, auto-meta para designators are only relative to a particular position. Is that okay? I'll show you what that is. It means that if we have two, so for example now, we cannot call this auto-meta para yet, except if I have OH, another OH here. So relative to this OH here, or relative to this OH now, this one is auto. Relative to this OH, this one is auto. This hydroxy is auto. Do you understand? I'll teach you how yet later, but just stick with me. So I just showed you this phenol. Now, another one you should also know is, what if I attach a CH3, okay, to my, keeping in mind that if the CH3 was here, it's still the same. If it's just one CH3, as far as one CH3, we only prefer to write it on top here. This is toluene, okay? Now, this one is called IUPAC nomenclature, IUPAC, we'll name it hydroxybenzene. While this one will be named what? Methylbenzene. Methylbenzene. Exactly. But this is the general, this is the common name. This is the IUPAC name. Exactly. Now, what if I have a molecule that looks like this, where we had only NH2? I'm still naming cases for one substituent attached. So in this case, this is called aminobenzene, okay? But the general name is, the common name is aniline. Is that okay? Aniline. Aniline. Now, in IUPAC nomenclature, we'll call it what? Aminobenzene, okay? Or it's also called benzenamine. Is that okay? Benzenamine. That's another way to name this guy. Okay? Now, how about if we have, I've used this, how about we have a nitro group on top? Okay? This will be called what? Nitrobenzene. Nitrobenzene. Now, actually, the full structure for this guy will look something like this, because here it doesn't depict that this guy has a charge, okay? But actually, fully, if you want to put this, draw the structure, which enables this guy to engage in substitution reaction, this guy is going to be structurally drawn this way with the double bonds. With the what's it called? The electrons on the oxygen, do you understand now? So it's going to have a negative charge. Do you get it now? So, I mean, it's going to be 1, 2, 3, 4, 5, 6. So, like this is the full structure, okay? But I just wanted to show you that that's the name, nitrobenzene. This guy enables this guy to engage in other forms of reaction, makes this guy very reactive, right? We have used nitro group. Now which other single guy can we replace? Okay, what if we have this? COH, okay? So of course, this is going to be what? Benzoic acid. Benzoic acid, all right? So in full structure, these will also look like, these are benzene here. These also look like this, double bond O and OH, C double bond O and OH, of course. Is it clear? So then that's benzoic acid. How about this guy here? What if we have a structure like this? Where we have CHO. Okay, this is an aldehyde group, right? So it will be called benzaldehyde. Benzaldehyde. Then, of course, if we have a molecule like this, that we have CHO. What if we have what if we have a methoxy group? Okay, a methoxy group. That is OCH3. All right, methoxy, right? Methoxy. So this is methoxy benzene, all right? But the common name, this is the IUPAC name, the common name is going to be anisole. Anisole, all right? So this is anisole. What if we have this? A vinyl group. What if I have a vinyl group attached now? An alkene attached. So I still have my guy like this, my benzene like this, and I have CH double bond CH2 attached. These will be called the general name is, the common name is styrene. Styrene. I think so. Styrene, yeah. And then there is xylene. Okay, I'm confusing it with this guy. Let's look at this guy. Look at this guy. Now, this is what you should now take note of. What you should now take note of. If I have this CH3, this is toluene, right? If I have another CH3 attached, like this is called xylene. It's called what? Xylene. Now, these will actually be orthomethyltoluene. Okay? Now, what that means is, toluene is already methyl benzene. Okay? So, this will be ortho I've not taught it. I'll show you. Just know the general name yet for now. Know the general name first. Now, what if I now have OH group? Now, there are various this thing for the OH group. If I have OH here, like this is phenol. If I put another guy here, this one will be called catechol. Okay? If I put amine group here, it becomes catecholamine. Now, if I put 3, now, this one is commonly confused by students. If I put this guy, if I put OH here, this is catechol. If I put OH here, this is meta position. If I put OH in this place, this one is called resorcinol. Okay? Resorcinol. Resorcinol is now different from this one again. Another guy here. Where if I have OH here, I have OH. Now listen to me. This structure is called quinol. Quinol. Or, quinol. Now, this structure I can redraw as this. This is what you should know. Know that I can redraw this structure like this, in as much as they are in opposite position. This structure I can redraw as this. I can redraw as this. Now, how many positions are these OH away from each other? There's just one carbon between them, right? If I put OH here, I just look for another OH. I just put OH here again. Just one carbon away from each other. That is also resorcinol. Or if I put one here, and I decide to put one here, that's also what? Resorcinol. Put OH here, resorcinol. Is that clear? In as much as just one carbon that is separating them. Therefore, para position, in as much as it's 2 carbons separating them, this is also what? Quinol. Is that okay? Then there is one more that I'd like to show you. It's called the pyrogalol. Pyrogalol that is used to isolate this guy, oxygen, industrial, this thing. So we have this. So this is pyrogalol. Alright. So these are some of the derivatives of this thing. There is also cumene, okay? Cumene. I've forgotten the structure of cumene. How does it look like? I think cumene will be 3. There is also cumene. I've forgotten what cumene looks like. Alright, let's go on to now the IUPAC nomenclature. Now, I'm going to first show you how to name on benzene, then how to name a molecule that has benzene as a substituent when benzene is a substituent. So let's clean the board now. Now, the first nomenclature I want to teach you is the one that uses the auto-meta para designators. Of course, I will also show you the IUPAC. Now, let me name xylene for you now. Xylene is the general name for, or common name rather, for this molecule. But actually, in IUPAC terms, this would be 1,2 dimethyl benzene, right? Now, using the auto-meta para designators, this is what you should know. That on benzene, depending on where we add substituents, okay, we have what is called auto position, relative to another position. So if I start from here, relative to this position will be called auto. So we just use O. This position will be called meta. We just use M. This position will be called para. We just use P. Now that's if we start from here. If our substituent is added here, let me use X for our substituent. Now what if I now have a benzene ring that I begin my X from here? If my X is added here, relative to this position, this place will be what? Ortho. Is that clear? The position, the auto-meta para designator is respect to how far away from the first guy. How far away from the first guy will be the major substituent or the functional group. Is that clear? So, if this is my substance here, then this one will be auto position to this. It means that it is just the adjacent carbon, a carbon away. Then this one here will be the what? The meta position to this guy. Then this one will be the what? The para position to this guy. Para position means opposite sides, opposite. This is para. Is that okay? Then all meta position is L. Once it forms L shape. Is that okay? Or L, upside down L or normal L, or like this. This is also what? Meta. Meta. Is that okay? Then auto position is just the next carbon, adjacent carbon. Alright. So since I'm assuming we know it now, let's name this guy using the auto meta para designators. This guy that we call xylene here, this guy, instead of 1,2-dimethyl benzene, we can also call it, this methyl is in auto position, right, relative to this guy, because it's just the next carbon. That is, the two carbons are just beside each other. So that will be auto methyl, no, O-methyl. This is where we put it. O-methyl. O-dimethyl, sorry. O-dimethyl. I think we put dash. We put dash, yes. O-dimethyl benzene. Is that okay? I think I've seen some people just put in bracket like this. Okay? O-dimethyl benzene. Now, what if I now have something like this? Now look at this one. If I have this, and you're asked to name this, and this one here is CH3. Now this guy, OH takes priority, so this guy becomes phenol. Is that okay? Phenol. So this should be carbon 1, carbon 2. So this is supposed to be 2-methyl benzenol. Is that okay? Because that's phenol. That's another name for phenol. Another name for benzene. See, benzene is also phen, okay? So if I put OH group, one OH group, it becomes phenol. When there is OH group, phenol with benzenol is phenol, phenol. So now say this is 2-methyl benzenol, 2-methyl phenol. Now if this is the case, how do we use auto guy? So it becomes O-methyl phenol. Now, what if I change it? Just watch. What if I change it? This is OH here, and I put my CH3 here. How far apart are they from each other? 2 carbons away. Once they are 2 carbons away, that's what? If my guy is here, then I have 1, 2. Second carbon. So then that will be meta. So this is M-methyl phenol. Is that okay? So it means that this guy, I can redraw it as this. This guy is the same, exactly the same as this. They are the same. Is that okay? All right. So that's to show you that it's just the position away from each other that tells us whether it is para, meta, or auto. Now, what if I have something like this? I have something like this. I have my OH here, and I have amino group here. Let's put amino group, let's put it here. Let's put chloro here, for example. Let's put bromo here. Let's fill it up. Okay? And this is benzene. How do you name this? Very easily. Now, which one takes priority here? Of course, again, OH group. That's priority. If there was no OH group, this one will take priority. Is that okay? So it takes priority. So this is phenol again, right? Or benzenol. So how do I name? Then I follow alphabetical order. This guy is C, this guy is B. So this guy comes first. Now, away from this guy, how far away from this guy is this? We just designate ortho position, meta position, para position, opposite. Is that clear? So if that's the case, this is meta position. So this will be M bromo, then C is the next. No, amino comes first. I'm sorry. A, B, C actually. So this should be what? Para-amino, meta-bromo, also chlorophenol. This thing is exactly the same as rotating this guy here like this. So what you would normally expect is this. OH should be here, the Cl should be here, the Br should be here, and the NH2 should be here. Yes, they are exactly the same. Is that okay? So P-amino, M-bromo, O-chloro, benzenol, okay? Sometimes we just use brackets instead of dashes. So I hope you now know how to name with those positioning. Now, what if we now have benzene as our substituent? Let me draw some shapes on the board. Let me draw some shapes on the board first. So I won't be taking time to think. All right, now let's name some questions, examples where benzene is acting as a substituent. Now, if benzene is acting as a substituent, usually you see what looks like this. Now, the name you use for substituent, for example, you remember if I have an R group, it's alkyl, right? Alkyl group. So, for example, if I have CH3 from methane, it becomes methyl, right? Okay. If I have C2H5 from ethyl, which is from ethane, which is supposed to be C2H6, this becomes ethyl, right? The same way here. When I have a substituent that looks like this, when I have a substituent that looks like this, this is benzene, this is phenyl, sorry. This is phenyl. Don't confuse it with phenol. This is phenyl group. So with phenyl group, you have C. How many C's do you have here now? You have C6. Let's see. 1, 2, 3, 4, 5, 6. But H is now 5. Is that okay? C6H5. Now this phenyl. Then if you now have one that looks like this, so that you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. C7H 1, 2, 3, 4, 5, 6, 7. H7 1, 2, 3, 4, 5, 6, 7. So if you have one that looks like this, C7H7, then this is benzene. Okay? So benzene, because there is an R group attached here, there's an R group attached here. Is that okay? So this guy, this whole thing, as big as it is, will be a substituent. Is that clear? So let's name this using that, what I just showed you. So to name this guy, of course, here the longest carbon to carbon change will be this guy. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Or we go this direction, 1, 2. This direction gives you the lowest possible number. So this direction is 2, so that will be 2. Now, is this phenyl or benzyl? This will be phenyl. Okay? So that will be 2 phenyl, 1, 2, 3, 4, 5, 6. Hexane. That's all. 2 phenyl hexane. In the case where you have other substituents, for example, let's say I have here, I have maybe C double bond OH, for example. This will become 1, 2, 3, 4, 5. So this will be, so the first one we drew was this. This one will be 2 phenyl still. No, sorry, this will no longer be 2 phenyl because COH takes priority. So we are numbering from here such that the COH takes 1, 2, 3, 4, 5. So that will be 4. We'll meet this guy on carbon 4. We'll meet this guy as a substituent on carbon 4. 1, 2, 3, 4. This guy is on 4. So we have 4 phenyl. 1, 2, 3, 4, 5. That's pentanoic acid. 4-phenyl pentanoic acid. Is that clear? Now, how about this one now? How do we name this guy? The molecule might just look weird. It's actually simple. It's actually simple. Now, looking at this guy, we'll name the longest carbon-to-carbon chain here is going to be either, now, which one is going to be the functional group? This guy is going to be functional group. So for that reason, we are using it. Is that okay? We are using it as functional group. So we are following the one that will contain this guy. We are using the longest carbon-to-carbon chain that will have this guy. So either we use this 1, 2, 3, okay, or we use 1, 2, 3, 4, 5. So this appears to be the longest. That 5, right? So that will be, if we go in this direction, OH will be on carbon 1, 2, will be on carbon 2. If we go in this direction, OH will be on carbon 1, 2, 3, 4, carbon 4. So we're using this direction. If we use this direction, this group will be on carbon 3. Now, which group is this? Looking at it, this is R group, and this is benzyl, right? This is benzyl. There is a carbon, an extra carbon attached to the phenyl group. So if that's the case, then this becomes 3-benzyl, 3-benzyl. Okay, 3-benzyl, 1, 2, 3, 4, 5. Pent, we will use 2-pentanol, 2-pentanol, or 3-benzyl pentanol. Is that clear? Pentanol. Now, what if I change this molecule to something like this? So, for example, I have something like this. Okay? Now, how do I name here? This will be 1, 2, 3, 4, 5. Let's say I even have OH here, for example. Now, this one I will also name with giving priority to this COOH. Okay? If that's the case, this will be carbon 1, carbon 2. We will hit benzyl on 2, then hit this guy on 4, this OH group on 4. So this becomes 2-benzyl. Now we have to use alphabetical order. B comes before hydroxyl. So 2-benzyl. Now, is this benzyl? No. This is phenyl. So don't forget that. This is phenyl. When the R group attached is just they're just one carbon away. Is that okay? That is, there's no carbon between them, between the benzene ring and the molecule. So that will be phenyl. So 2-phenyl, pent, right? And no, there is also another group here. 4-hydroxyl, pent, so let's put a dash here, pentanoic acid. Is that clear? All right. So let's name this guy. So the name of this guy, I'll put that here. The name of this guy is going to look like this. Of course, you can already count the longest carbon chain. 1, 2, 3, 4, 5, 6. Check my video on alkyne to understand why I did this here. 1, 2, 3, 4, 5, 6, 7, okay, 8, 9, okay, 8, 9. So the longest carbon chain here is 9. And if we count in this direction, we'll meet the triple bond on 1, 2, 3, 4, 5 on carbon 5. We'll come from here 1, 2, 3, 4. We hit on 4. So we are coming here because if we come here, we'll hit this guy on 3. So it becomes 3. Is this phenyl or benzyl? This will be benzyl, right? So 3-benzyl, 1, 2, 3, 4, 5, 6, 7, 8, 9. No known, or 3 or 4-9, benzyl 4-9, or 3-benzyl nonaphorine or nonaphorine or something like that. So that's that. On this one, now this one is also simple. What will be the longest carbon-to-carbon chain? Now it's going to be this. This benzene will be what? A substituent. So here, to name this guy, we'll number from here or here. Now, which direction will give these ketone groups? So this is a diketone. So we have 1, 2, 3, or 1, 2, 3, or 1, 2, 3, 4, 5. No. So this is the best direction. 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5. Okay. So either way, this guy keeps falling on 5. Then 6. So there are 6. This is a 6 carbon ring. So we have now is this phenyl or benzyl? This is phenyl, right? So this will be 5 phenyl, 1, 2, 3, 4, 5, 6 hexa 1, 3 dione, or 5 phenyl 1, 3 hexadione. Okay, so that's that. Now, I also have reach out to me on that WhatsApp number if you want to learn more namings. You want me to send you questions on naming. So, then of course here, to name this is also very simple. This is going to be the same way. The longest carbon chain is also here. Okay, but this is benzoic acid, right? This one is benzoic acid. So this is going to be benzoic. So it is 1, 2, 3. If we go like this, 1, 2, 3, 4, 5. This one will be on 4, on 5. If we go like this, 1, 2, 3, it will be on 3. So it will be 3. What's this? This is benzyl. 3 benzoic acid. 3 benzoic acid. So that is it on nomenclature. Now let's move on to, we've done nomenclature. Let's move on to synthesis. Yes, let's move on to how do we prepare benzene? Synthesis. Alright, so let's talk about the general method of synthesizing benzene. So I like to do this quickly because the video is already long. I'll just quickly rush you through the general method of preparation and the physical and chemical properties. Now for general method of synthesis, the first way is to synthesize from an alkane. We can synthesize from an alkane. So the process is called aromatization of alkane. Aromatization of alkane. Okay, I have discussed this a little bit in alkane. The process begins with initiation, polymerization, and initiation, cyclization, and aromatization. So for example, our normal hexane will go in the presence of Cr2O3. These are the things you are most likely to be tested on. The catalysts, Al2O3. Okay, so what happens is in the presence of intense heat of about 600 degrees Celsius, you make benzene. From N-hexane, exactly, normal hexane. So you can also synthesize benzene from alkyne. Okay. The process is called cyclic polymerization. I wanted to misplace this. So this one, the 3 steps, I said initiation, then there is cyclization, followed by aromatization. So that's that. Now for this guy, in this guy we have like for example our hexine, for example now. From hexine, also in the presence of heat, we use red hot tube, okay? Red hot tube. So if we have hexine, 3 molecules of hexine, 3 moles of hexine, is going to turn to benzene under intense heat as well. So that's alkyne, using alkyne. Another process, another method is deoxygenation. Deoxygenation of phenolic compound. Okay, of phenolic compound. So for example, if I have normal phenol here, now if I react it with zinc in the presence of heat as well, what will happen is zinc will remove the oxygen, it will deoxygenate it. And what are we going to form? We'll have our benzene. Is that clear? We'll have benzene, of course, and zinc oxide. So it's reduction, okay? It's a reduction process. A reduction of phenolic compound, okay? Of phenol. Now, why do you say phenolic compound? Because it could be methylphenol. So, for example, if I have this, now this should not confuse you. This is not toluenol. This is still phenol, but now orthomethyltoluene. Orthomethylphenol, exactly. Orthomethyl, because methyl is just a carbon away from it. Orthomethylphenol. Now, still reacts with what? With zinc. What does it do? Abstracts the oxygen, and then we have what? Our toluene in this case. We form toluene. Exactly now. We form toluene plus zinc oxide. Shout out to my girl that bears Tolu. Toluene. Okay, so number 4. We can also prepare it by decarboxylation. Decarboxylation. So when you hear of decarboxylation, I've told you in the alkane video, when you hear decarboxylation, what comes to mind for any organic compound? It means there is an alkanoic acid, right? An oic acid at the end of the day. So in this case, benzoic acid, of course. So if you react benzoic acid, how do you now? C double bond OH. Now what happens is that we remove this guy, okay, and we have we have our guy here, benzene here, plus CO2. So that's the carboxylation. It means we are removing carboxyl group. Then there is also the last one, which is use of Grignard reagent. Use of Grignard reagent. Now that is if I have a Grignard this thing attached to this guy, so to benzene. So for example, if I have what looks like this, what does Grignard reagent look like? RMGX. So in this case, you have Mg, maybe Br, for example. What will happen is that this guy is a good living group. It leaves, and when it leaves, what happens? Hydrogen will be added to this guy, and then will form benzene. Is that okay? So that is the general method of synthesizing alkene. General method. Now, let's talk about the properties. So the physical property, it has normal melting point, but a high boiling point, and it is less dense than water. And what else about benzene? It has a Since of course it is aromatic, right? It has a nice smell, and but it's colorless. It is colorless. Those are physical properties generally. But let's talk about the chemical properties. Which are the ones you are most likely to be tested on? Chemical properties. Now the chemical properties begin with, of course, it can undergo combustion reaction. Combustion reaction, which will be C6H6 plus O2 to give CO2 and H2O. This is complete combustion. But incomplete combustion will be ozonolysis. Ozonolysis. So if it undergoes ozonolysis, very simple. What you do is just do like this. So I'm going to draw one composite and I'm going to draw a contributing distance so that you see what happens. I'll clip the bond here. The normal way we do ozonolysis, clip the bond here, put OO, clip the bond here, put OO. So what will I form? I'm going to form CHOs, many CHOs. One CHO here, CHO bonded to another CHO, like this. It should be like this and like this. Okay, so this is what we're going to form. We're going to form these in how many? How many places? This is 6 carbons, so that will be 3. 3 of this. Do you understand? When this guy reacts with ozone, okay, plus ozone. Now, this is incomplete oxidation, so that's how to. This one is complete oxidation, that's combustion. Then number 3, reaction with. So generally, you should know that the general reaction of benzene is called electrophilic substitution reaction. Or you might hear electrophilic aromatic substitution. Okay? Right. So, but it can also undergo addition, but it needs very strong catalyst to do that. Very strong catalyst. So, for example, if you react benzene with halogen, so let's start with halogenation. If you react benzene with halogen now like this, okay, it has to be happen in the presence of UV light, okay? In the presence of UV light, you form what? A free radical, right? So it requires that free radical to be able to break this bond. Otherwise, now, if it happens in the presence of this, what happens is a substitution reaction. So this product I want to write is substitution product. So if it's a substitution product, what you will see is this without the presence of UV. If not in presence of UV, what you will see is a substitution product. The substitution product will look like this. One of the H's will be substituted by Cl, so you have chlorobenzene. Is that okay? You form chlorobenzene. But if the reaction happens in the presence of UV, ultraviolet radiation, you know that there will be homolytic fission, which will give rise to free radical, chlorine free radical. So plus Cl in the presence of UV, so there will be what? Free radicals produced. So free radicals here are very reactive. So what will happen is that they will an addition product to be formed. So the full addition product is what I'll draw here. It will look something like this. Cl. The same is true for bromine, okay? With a bromine that was also reacting. Okay? So, okay? And so this is called what? This is called 1, 2, 3. That will be it's called 1, 2, 3, 4, 5, 6, 7. It has a name as I think lindane or something because it's used for um, it's a powerful insecticide. You understand? All right. So um, so that's in difference of that. That's the addition product. So what of another substitution product? What of hydrogenation? Hydrogenation also in the presence of catalyst. Hydrogenation in the presence of I've forgotten which catalyst, but under intense temperature of about 220 Kelvin, you also have N-hexane for hydrogenation. Hydrogenation. Okay, so that's benzene hydrogenated to N-hexane. Then there's also the Friedel-Crafts alkylation. There's one more I want to. Okay, there's also nitration and sulfonation. Okay, there's nitration and sulfonation. For nitration of benzene, what you basically do is this benzene, you react it with HNO3 in the presence of H2SO4. Okay, and also intense heat, about 320 Kelvin. By the time you get this, you do this, you get nitrate, nitrobenzene, NO2. Is that clear? So, and of course, sulfonation occurs in similar way. Just the reagent is different. So in this case, you still have this sulfonation. That's what it's called, sulfonation. You have your benzene. Benzene reacting with oleum. It reacts with oleum. And what is oleum? That's H2SO4, okay, plus another SO3. So that's this oleum here. And the rest of intense temperature also, you get SO3H. So this sulfonated oxygen. Or sulfonated benzene. All right. Then Friedel-Crafts reaction. Friedel-Crafts. So there are two persons, okay? Friedel-Crafts. I'm going to show alkylation here, okay? Now it's also a electrophilic substitution, okay? It's an electrophilic substitution. So what will happen is that in your benzene molecule where you have an hydrogen here in this case, you will have an electrophile, let's say for example, CHBr, for example. So what will happen is that this guy leaves as a living group, leaves this guy as a carbocation, but the carbocation is not stable. So let's use one that will form a stable carbocation plus CH3, CH2, CH3. So what will it form? What will happen is that CHBr rather. So when this living group leaves, it forms a stable carbocation. What will happen is that there will be a rearrangement. So it follows a rearrangement to form a secondary. There's a rearrangement to form a secondary carbocation. So after that rearrangement reaction, then what you have is CH3, CH plus, and CH2. Do you understand? Then after that, then this one is now what you now join with this guy. We abstract this guy, and then you form this. So this is alkylation. I've told you about alkylation in this thing. CH2, CH, CH3. Oh, there was something I wanted to remember then. Cumene. The structure of cumene is this. This is the structure of cumene. Let me draw it here. So if you have isopropyl benzene, that's cumene. Okay, so add it to your common names, the list of common names that you made. So this 1, 2, CH2, CH2, CH3. So this is going to be the product of alkylation, Frederick Kraft's alkylation. Alright, so this will be it for this video. Do want to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. Now, if you need more on either any of this part that I've explained, because I know I didn't do any mechanism here at all, and I normally do it, but it's because of tiredness, okay? And today is Christmas, I'm supposed to rest. So reach out to me for any part I'm going to re-explain further, especially these parts. This addition reaction, maybe ozonolysis. Ozonolysis should not confuse you. And even the Frederick Kraft, there is alkylation and acylation. Alright, do also subscribe to the channel.